Hey everyone, welcome to this webinar. My name's Daeil. I'm the technical founder of AI.Reverie. And what we do at AI.Reverie is to create a synthetic data platform for smarter products. So super excited about this particular webinar because there's three things we really want to showcase here. The first, we want to actually share with you the latest data technology that will get you to produce computer vision algorithms faster using synthetic data. The second thing, though, is we really want to highlight a lot of cool insights from the research for our new head of machine learning, Aayush Prakash, who just joined us recently from NVIDIA. And finally, what we also want to do is want to hear your questions and feedback on synthetic data. So there's going to be a live Q&A after this, and super excited to be able to answer some of those questions. So without further ado, I'd love to introduce our head of machine learning, Aayush Prakash. He joins us again, as I mentioned, recently from NVIDIA, where he's focusing on really cool emerging ML techniques such as structured domain randomization and scene graph generation that we'll talk more about today. So welcome, Aayush.
Hey Dale, thanks for having me. It's really great to be part of the AI.Reverie family.
Well, we're glad to have you as well. So, I know you joined our company while everybody's still at home from the pandemic and attending webinars, but excited to have you here to be able to share this great knowledge.
Yeah, it's a testing time for all of us, but at least through this webinar, I can connect with them, all the people who are working from home. And hopefully this is not the last webinar.
Yeah, definitely not. So so let's just get into it. I mean, you spent the last 5 years at NVIDIA, focused on synthetic data. Tell me a little bit more about what gets you excited about it, why you spend so much time focusing on this problem.
Yeah. So supervised learning problem, where when networks are trained on real data, it's not really scalable with the current state of the art technology. And the main bottleneck in the midst of the supervised learning is actually the data. So real data is actually hard to acquire, and even the labeling process is very expensive and time consuming. To give you a concrete example, if you actually have if you're doing instance segmentation for a perception task like instance segmentation, if you were to label it for a large amount of data like 100,000 images, that will take months or years to even get it done.
Yeah.
And that's where synthetic data really appeals to me. Synthetic data actually it is a great solution. It's a very exciting and great solution. And data acquisition is such an easy problem. Like, if you want to do instant mask, if you want to segment the instant segment, if you want to segment the images with instance mask, it's very easy to do. And on top of that, even tracking problems, it's very easy to get labels for all of this.
Yeah, so there's a lot of interest in synthetic data recently, but there's also, we're believers in synthetic data, but there's a lot of skepticism as well. And I'm sure you've encountered some of that in NVIDIA, right? So could you talk a little bit about, what it takes to make synthetic data work in the real world, right? Like, what is it that we really need to get right?
So that's a great question, right? And I understand the skepticism around it, and I understand that I'm with the skeptics here, right? Synthetic data has come a long way over the last couple of years, and for simpler problems like segmentation problems, like road segmentation, or if you want to do road sign detection, right? These are simpler problems. For these, synthetic data work really well. But when you look at some harder problems, synthetic data has harder problems like like driving scenarios and all kinds of perception problems there. And when complex indoor scenarios, synthetic data hasn't really performed as well so far. I understand the skepticism around it, and I've seen the work that AI.Reverie has done. They have constantly developed a lot of tools and technology to actually address some of the long-standing issues. One of the things that keeps synthetic data going is the recent advances, in the rendering technology, like rendering engines like UE4, and because it enables to have really photorealistic captures. And there has been a lot of work also around content creation for AI. that addresses some of these synthetic data issues.
Definitely. And so, Aayush, being at NVIDIA, you've done a lot of good research when it came to synthetic data. Could you highlight some of the really cool papers that you really enjoyed working on and talk a little bit about that to some degree?
Sure. So one of the so I'll give a little bit story about how I got into synthetic data to start
Yeah,
that
that'd be
question.
great.
So
Mm-hmm.
what happened is, I was working in a robotics domain, and I had a robot, and I wanted to train the robot to recognize some domino pieces right on a table,
Right.
and there wasn't a real data for this, right? And if I were to go and take some pictures myself and then ask data factory to annotate it, that will take weeks. The timeline I got was like even months, right, for getting these things annotated, because data factory has other workload and things like that. And for me, I wanted to solve that problem. And even if I got all the real data from the data factory, the environment where the robot was to be deployed was very different. Like, it's going to be very different from the training environment. So what we did was we got a bunch of simple domino models, randomized everything, and then trained our perception module on that synthetic data, and that performed really well. And what I found, that's when first I saw the really compelling power of synthetic data. So and that got me hooked into synthetic data, because all the problems we faced in real data. And I started looking into doing research into what sort of synthetic data is right for training these perception modules. And the first work, one of the earlier work we did, was around randomization, right? And the key finding from those randomization was that even if you create an unrealistic scene, like for example you want to detect cars in real world, synthetic data, you can create unrealistic scenes of cars with cars flying in the air, random number of cars, no context, no background. So you're not really actually fully simulating the car scenarios. You're just randomizing everything in the scene. So texture, color, number of light sources, amount of intensity, it was all very unrealistic. And doing all this, we found that we were able to train detection module for car, which performed really well in the real world. And in fact, it came very close to performance of other fully simulated synthetic data sets. So that was a
Yeah,
very good insight we got from randomization.
right.
Second thing, one of the second work, interesting work that I did as part of NVIDIA was, this work where can we automatically create synthetic data sets which can match the distribution of real data, such that we get optimal performance on downstream tasks. So the idea being, you bring in your unlabeled real data sets, and I'm going to say create synthetic data that matches the distribution of real data, or that starts to resemble this real data automatically. So to me, these were the two key interesting work I did as part of NVIDIA.
Well, it's cool because with robotics, synthetic data is really, really useful in many ways, right? Because the kind of annotations you find in robotics for computer vision is quite complicated. It's no longer
Yeah.
just simple 2D bounding box. You might also want to understand the pose and the perfect pixel level segmentation and all of these different types of annotations that allows a robot to help grasp something. So I can imagine when you're encountering this problem, you're like, yeah, synthetic data starts to feel like a really, really good solution. But I also see a narrative with this story as well. So you talked about domain randomization. You talked about how you were just trying to randomize things. But then you started talking also about a more structured approach, right? So in some ways, you're sort of finding that domain randomization was good, but not enough to get to the last mile. Could you sort of elaborate a little bit more on that, on sort of that transition from working on things around domain randomization and then transitioning to something of a more structured approach?
Right. So that's a great question. So yeah, randomization, creating unrealistic scenarios and everything that gave performance, and that was very easy to create synthetic data sets, and it gave a good performance. However, that was not enough to close the performance lag. Right. It was not enough to perform as well as real data sets. So that got me thinking around, more can we do? That led to a creation of a system called structure domain randomization, which where we started randomizing objects and texture and other things or components in the scene while within the realistic values. For instance, cars won't necessarily fly in the air; they should stay on the road. So they will be randomized on the roll among all the probable values. The texture on the cars will be random, but it will be within the permissible, textures that are available in cars and things like that. So that gave further improvement and that performed very well even in like complex scenarios where we had lots of occlusions and lots of challenging environments where the objects were very hard to detect even for human eyes. So that was a more structured transition. And after that, what happened was, we wanted to improve and push the boundaries further, right? And we wanted to actually really, really perform as close as possible to real data. And that led to the thought of, randomization is great. That works great, whether you do it realistically or unrealistically, but let's try to really clone the real data, right? And really bridge the gap between synthetic and real data. And in order to bridge that gap, we came up with other techniques while working at NVIDIA on how to automatically do it. Because most often, graphics designers or software engineers, when they want to create synthetic data, they would actually, create a replica or a digital twin of the real scenes, and that's very expensive. So I started working on methods on how to create these digital twins automatically, with the goal being that we really bridge the gap between synthetic and real data and just outperform real data.
Yeah, no, that's great. And part of the work you also have done around the sort of structured part is this notion of scene graphs, right? And scene graph generation and learning scene graphs. I think this is a really interesting area of research with a lot of possibility. And I know you spent a lot of time thinking about this. Can you first tell the audience like what a scene graph is and why that's important and how you think it can help reduce the domain gap, as we're calling it in computer vision, between synthetic and real world data?
Yeah. So a scene graph is a structural representation of the scene. Now, in simple words, what do I mean? It's just represents what are the objects in the scenes, where they are located, what rotation or what pose do they have, right? What texture exists on these objects, right? So essentially, these scene graph are a representation, a textual or a graphical representation of these scenes. And these scene graphs can be fed into a generation system, which will be a rendering engine to actually create a scene out of it, right? So that's what scene graph is. And I think it's extremely important to understand, what are the real scene graphs are, right? For example, when we bring in real data, right? Can we extract scene graphs from it, right? Which represents these real scenes. And then once we have this scene graph, this is a domain agnostic representation. What I mean by that is that a scene graph is gonna look the same whether it's real or synthetic. It's sort of a domain invariant representation. And you can extract these scene graphs from the real data because and then these scene graphs will be fed into a rendering engine, and then we'll be able to create synthetic scenes that match the scene structure or the scene graph of real data. To me, that will bridge the gap that we are seeing, and I think it's one of the recent advances in addressing the gap between synthetic and real data is to extract these scene graphs which match the real data and create synthetic scenes which from these scene graphs.
That's great. Thanks for that. I think that helps clarify what it is. And there's a lot of good research coming out in this area, and I think it's going to be very helpful in helping folks understand what that domain gap looks like. Just to sort of keep going a little bit further along with this, when it comes to academics, there's a lot of people who work on synthetic data. What do you think are some of the biggest bottlenecks that, when it comes to people in academia trying to do research in synthetic data, that they encounter, given that that's your background and your experience as well?
So that's another great question. Yes, people doing research in synthetic data, they often suffer from the lack of or availability of simulators or synthetic data generators. And while there are open source simulators like Carla and whatnot, these are very hard to always adapt to the situation that researchers care about. So there's a general lack of general simulators which can adapt to any kind of scene. And then on top of that, there's also lack of assets, right? Like 3D objects, right? Which researchers often find it hard to get access to, right? AI.Reverie has done actually a great job developing some of these tools where you have these really general simulators which can actually randomize or match the scene graphs of real data in different situations, right? Whether it be driving scenario, whether it be whether it's driving scenario, whether it's retail, whether it's smart agriculture or any kind of environment. AI.Reverie has done a great job developing these simulators, and then they also have access to a vast amount of assets, and they're also working on some proprietary technology to actually create these kind of assets. Let's have some examples of some of these some of the things that AI.Reverie has done. So as you can see here, there are a lot of diversity in a driving environment. AI.Reverie can annotate everything. This is an instance mask example, but essentially anything can be annotated in synthetic data, and there's all kinds of diversity that's present here.
Yeah, we certainly have worked on a lot of really interesting problems, and you can sort of see that some of the work we do is in procedural generation. So we spend a lot of time thinking about creating asset diversity, not only by acquiring assets through an ingestion pipeline, but also to do it procedurally through our own proprietary tools. And I think that's going to be a big thing in the future. One of the biggest bottlenecks of synthetic data is a problem we have to solve. So. But you can see the power of the rendering engine that we're using. A lot of our work is built on top of the Unreal game engine. So this is a really exciting area. And Aayush, thanks for showing us some of these screenshots. I'm really excited about them as well.
Yeah, and look at the diversity as well, like all the retail diversity. Like it's amazing. It's great. The diversity that you guys have achieved.
Yeah, and the hope is that we can sort of productionalize this, right, and make this into a product that can serve anybody who has these types of computer vision challenges, because there is so much work that goes into making these kinds of, product platforms usable and to create the diversity needed for these scenes. So I'm super excited about sharing that with everyone. And if you want to learn more, you can always, of course, go to our website or email us at hello@ai.reverie.com. But moving along, we talked a little bit about this asset diversity thing, and I know there's some really cool research as well on top of that in the area of neural rendering. So I want to get your thoughts on that, and there's some really cool stuff there. I want to hear what you're excited about in that area.
I think some of the work that is happening is fantastic, because even for synthetic data companies like AI.Reverie, it can be expensive to even with procedural generation and all the cool work that the company has done. It can be very expensive still to create models or to buy models or things like that. So this is extremely exciting if we can create these meshes, these objects, 3D objects automatically from real data, right? And with some cheap annotations. I think it's a very exciting directions. At AI.Reverie, I think we are also planning to invest some of this, invest in this technology.
Definitely, and because it is one of the significant bottlenecks of synthetic data is to get asset diversity, but it's also an important one to solve in order to help minimize that domain gap. So that's very exciting. Aayush, is there any other research areas that you want to talk about that you think are really exciting, or things that you think you're excited to spend more time thinking about?
Yeah. So let's talk a little bit about this domain gap that we have discussed and match it, right? So this domain gap happens, when you train your AI models or neural network models on synthetic data. and when you test it on real data, you have this sort of gap, domain gap, right? So how do we address this domain gap? And some of the work that we discuss around randomization, or around matching the distribution of real data, or even extracting scene graphs from real data, and trying to generate synthetic scenes that match these real scene graphs. They address some of the domain gap, right? And but there's still some gaps that remain to be addressed, right? And at AI.Reverie, we would definitely like to first break down this domain gap fundamentally into further components, right? Like, what is it that really comprises this domain gap, right? And then try to address each of these domain gaps separately. Where you have different, for example, typically domain gap is divided into appearance gap, like how they differ, and content gap, how much the content is different between the two scenes, right? But can we break down content gap further, right? And after breaking it down, what are the approaches can we develop to address each and every subcomponent of this content gap? So these are some of the things that I want to work at AI.Reverie on, because this domain gap is the fundamental problem which is really holding back synthetic data. And once we really address it, I think real data maybe even completely redundant at that point, or it's not going to completely go away, but at least that's the vision we share at AI.Reverie. That let's try to address this domain gap, and we have some ideas on how to address some of these gaps, and we're working on some proprietary technology that hopefully will address this domain gap in a near term or short term for
So
most of the domain.
it sounds like what's important is fixating the problem towards this domain gap, right? With synthetic data. When it comes to this, we have to sort of quantify and understand how we want to break this down into sub pieces, into sub modules, and to create tools around that, so that we're able to measure that and to be able to sort of know what kinds of things we do help minimize that domain gap, right? Is that sort of to some degree a way of summarizing what you're saying?
Yeah, that's exactly what I'm saying. Like, trying to understand these different components and trying to develop work, right? For example, a lot of work has happened around, let's talk about appearance gap, right? A lot of work has happened around image translation, right? Where we translate day to night images, where we translate synthetic to realistic looking images, right? They work great from a human perspective, right? Where we see them, oh look, they start of to look real, or things like that. But if you dive more deeper into how these networks work and how good these translations are, more often they don't just work, right? And at AI.Reverie, we are looking at multiple domains. So at one domain, even if some of these techniques can work, if we switch to other domain, it doesn't work. So we're some of the problems as we are looking into is to how to address this domain gap, to address this domain generalization scalability issue, right? How to address this domain gap at scale, so that it works for multiple domains and it works more reliably than the current existing research.
Yeah. And doing things at scale creates additional challenges, right? So it's one thing to create a little project on the side and be able to use synthetic data to solve that. But to make it into a product and to be able to create something that can scale to hundreds or thousands of people all at once is definitely certainly another challenge. Going back into some of the use cases of synthetic data, Aayush, is there any particular use cases that you think you're really excited about, like where you think the value of synthetic data is so valuable?
Yeah. Where do people typically use synthetic data right now, right? When they don't have enough data, right? Or their data acquisition is very expensive, or they it's very hard for them to get data or to label it and things like that. Synthetic data also shines when we want to create rare scenarios or rare kind of objects, right? Or address this class imbalance in real data, right? Because it's very hard for real data to just capture all the diversity and all the scenarios. It's just not possible. Like, yeah, you can if you want to grab some driving scenes, you can mount a camera on car and then start driving it around multiple places and all possible places. I can still bet that you would still not be able to capture every scenarios, every weather conditions, every possible pedestrian placements and things like that. So that's when synthetic data really shines, where these rare classes, they just don't occur when you decide to take the captures, or these rare scenarios. You cannot just stay there for some rare event to happen. That may take months, years, who knows.
Absolutely.
Yeah.
And this is sort of what they refer to in computer vision as, like, why they talk about it as a really long tail problem, right? So you might be able to get a certain amount of data and get 80 to 90% of what you need from the initial
Yeah.
data set. When it starts going into that long tail, the sort of sheer complexity of those problems and all the different kinds of permutations and things you can't account for in that long tail, it suddenly becomes a very expensive procedure in order to get it to mission critical performance. Would you agree with that?
I agree with that because, in fact, to me, if you ask me, to me, the tail end of this distribution that we're mentioning is more important, much more important than
Right.
than just the mode. Because most data that exists, even data that that people have released publicly for benchmark, they sort of work in these mode of the distributions, or these most obvious scenarios. But when we are dealing with safety critical systems like self driving, we really cannot afford to make mistakes, right? And then that's when this tail end of the distribution is extremely important. And then synthetic data is an acceptable answer to addressing that issue.
Yeah, and one of the things that I've also heard is that how synthetic data could not just only be used for the traditional ways of cheapening the costs of collecting labeled data, but also it could actually be used in the future as a way to test and evaluate real world algorithms, meaning algorithms trained on real world data. But there needs to be some kind of performance that it must achieve in these certain edge case scenarios that we've just been talking about, right? What do you think about that, Ayush?
Yeah. So you bring up a good point. Synthetic data as a testing situation, right?
Exactly.
So think of robotics environment, right? Robotics community really lacks data. We could talk to robotics researchers. They're always telling us, where is the data? We don't have data, right? So let's say we provide them data, right, and they're able to train their models on the data that we provide. Even then, testing is extremely crucial if they want to deploy their robots in real world. It's actually limited by real world testing, right? Like you're going to have to wait. If a testing required 12 hours, you have to wait and deploy the robot in that environment for 12 hours, and then just to sit back and see what happens. However, if you test it in synthetic simulation or synthetic data, you can go thousand, even much more higher speed, because the only bottleneck at this point is compute, right? If you have any number of hardware or GPUs, you can go create as many testing environments. So you can really speed up this testing. Second advantage is also like testing in again these rare scenarios, right? Like, are you going to keep deploying robots in these most common scenarios? But what about these rare scenarios that can happen when somebody comes in the front of the robot, right, and or some unseen objects, right? So even for these from a safety perspective, and creating these rare scenarios for testing or your neural network model, or robotic learning is extremely crucial. And I think synthetic data is a great answer for this.
I mean, and also another thing I just want to add is what's really interesting about synthetic data, especially if we're using it within the supervised learning framework, is that assuming that supervised learning is still a predominant way of training deep learning algorithms, there is a case to be made where at some point the annotations, there's a limit to what humans can annotate. When we start moving from just 2D bounding boxes to segmentations with things like activity labels with skeletal pose, or even annotations that humans can't infer, like the weight of an object from a 2D image. I mean, it just seems to me that over time, if we want to push the boundaries of computer vision, how do we do that with real human labels? Where is the end point? At what point can we say that this is good enough if we want more sophisticated algorithms?
That you bring in an excellent point, right? So sure, we have talked about so far is detection and segmentation, right? But like activity recognition, right? So full or object tracking, uh, or even things like annotating 3D objects, right? Or 3D scenes and things like that, or doing 3D kind of annotations. um, it's extremely hard for human annotators to actually achieve it, right? And often, even with the best guidelines that most companies create for these annotators, there's still a huge amount of noise that happens, right? So not only is time consuming, right, and it's very hard to annotate, and and it's almost difficult for them to be consistent. They end up creating a large amount of noise, um, and that noise is not good or not great for you training your models, right? With synthetic data, we guarantee correctness, right? We guarantee any kind of annotations, and we guarantee correctness, and we guarantee consistency,
Yeah.
and that's one of the winning areas for synthetic data.
And people, there was a recent paper out there was an article in MIT Technology Review that talked about
Yeah.
ImageNet performance, right? About how if you were to actually correct the errors in the ImageNet data set, you can use a much cheaper model to get the better performance and a much more robust, more architecturally intense model, right? So that's it just shows you how important errors can be, and how it can actually really affect algorithmic performance. So definitely excited about the future of synthetic data there. Now, let me ask you a question as somebody who's been in this field for many years. If you want to sort of give advice to people who want to enter this area of research, what are some of the things you would tell them? Like, how would you sort of mentor them? How would you sort of guide them to get more interest in synthetic data? And how would you help start them off?
Yeah. So advice for engineers and researchers will be slightly different, right? For engineers, I think uh, synthetic data is not something you can conjure over a couple of days and it's going to work, right? It's a deep tech. It requires some expertise and some knowledge. So availability of simulators, or of tools or things which can actually really outline the gap that exists, so that you can focus on the right problems, right? You can focus on the right gaps. So the right tools, the right engines which can create synthetic data. Maybe some of these engines can actually design such that they address the domain gap better than the others. And some kind of analysis tools that if it's open source or if it's something they can develop to understand this domain gap and try to bridge it. I think bridging this domain gap that we spoke of used to be very difficult. A couple of years back, used to take a long time. But now with better toolings, especially the ones we are developing at AI.Reverie, you can bridge this gap faster, much faster, and use these tools to actually bridge the gap. The advice for researchers would be, it's an exciting area of research, and there's still a lot that needs to be done. And I definitely urge the researchers to understand some of the state of the art, go through some of the state of the art. There is a lot of work that has been done on synthetic data. Understand where the bottlenecks are in domain gap, and try to come up with methods to bridge a domain gap. And obviously a general solution is going to take time, and you don't have to create a general solution, but as long as you start bridging gaps in your specific scenarios, I think that's the way to go about it, and hopefully help your fellow by developing good methods, help your fellow robotics researchers to get this data.
Well, on that note, I want to sort of ask you what future areas, given that we're talking about giving advice to future researchers on synthetic data, what specific areas excite you the most? Like what kinds of research topics within synthetic data get your ears tickled when it comes to really promising ideas and solutions?
Yeah, there has been some work, recent work where you're using GANs to actually generate synthetic data. I think that's an excellent direction, where you can use GANs, to generate both the images and the labels, right? And you require very little supervision to train such models. An example of such models is semantic GAN and data set GAN. I have also worked on a technique to use GANs to actually generate synthetic data and also get labels from it and train models on it. What we found is that the performance is quite competitive compared to rendering engines, or where costly rendering engines or entire simulations. It actually performs competitively to that. In fact, in most common situations, it even outperforms the mode of the distribution that we're talking about. To me, that's a very exciting area, and I think that's something I'll point out.
Great. So I hope we've given attendees a clearer picture of how synthetic data works and how it can boost ML performance. So let's take some time for questions. You can submit questions for using the chat button below this video, like a regular Zoom meeting. So thanks for coming by and looking forward to what your questions are. Hi, everyone. So I hope you all enjoyed the conversation that Aayush and I had. And we'll go ahead and try to answer some questions from the audience. And first of all, thank you all for attending this talk and for submitting your questions and for staying on. We'll try to get to as many of the questions as possible because there are a whole bunch that people have submitted. So we'll go ahead and get started here and then discuss them in more detail. So just to get us started, one question that I think is worth sort of talking about, it comes from Alexi, and he says, what is exactly the input you will need to generate a scene graph from fixed camera video? Will a single frame be enough? Probably not. Will you need all camera parameters? And I think this is a good question because we can help articulate and help clarify our scene graph approach or the scene graph approach and what we're trying to sort of go at here. So Aayush?
Yeah, so that's a great question, right? Like you mentioned, Dale. If one scene or one frame is not enough, sure, you can learn that one scene and then you can add some randomizations to it, but the performance is going to be limited, right? And ultimately, we want to learn the distribution of say real data, and to learn the distribution of real data, we need enough real data. And when I say enough real data, I don't mean annotations per se, right? I just mean, unlabeled images, right? Real images. And they can be available in plenty. Usually they're very cheap to acquire. We're working on devising techniques where we can look at, lots of unlabeled real images, and we can, using synthetic supervision and some kind of distance metric between synthetic and real, we are trying to figure out how to extract these scene graphs from real. In terms of the camera question, I think knowing camera parameters is going to generate more accurate scenes. Not knowing it is okay too. You can actually approximate it by making some assumptions. For example, when you actually see driving scenes, you can assume that the camera stays either on a dash cam or on top of the car. So with those fair assumptions, we can still get very close. And ultimately, the more supervision you provide, the more annotations you provide, the better we can get. But if you don't, we can still get a decent performance.
Great, awesome. All right, and we have a lot of questions here, so we'll try to just get to some that are, that we can sort of help answer. Now, another question that is asked is, how can we actually measure performance models trained with synthetic data in case models have been trained with real data don't exist, right? So this is a question that where you don't have real data. How do you assess the goodness of this? I use your perspective, and I'm happy to pipe in as well.
Yeah, that's a good question. I mean, Usually we require some validation sets, or some test sets to actually get the quantitative performance, right? And if we don't have that, we can get somewhat clever, right? We can actually, for example, have just take the qualitative understanding of it, like go test the model based on real data, directly deploy it in your real environment, and then and then see how it's really behaving. How many false positives are you getting? How many false negatives are you getting? How well it's performing? So so that's one approach. And you can even give it out to a bunch of people, like a randomized study, and then see that if this is something acceptable to these people. So
Yeah,
that's sort of what I was thinking.
yeah.
I mean,
I
the
want
other thing is, go ahead.
to. Oh no, I just wanted to highlight that for some academic papers, when they don't have that kind of real label data set to validate and benchmark against, they use these sort of Inception scores, right, to just sort of see the
Yeah.
difference and what realistic it is and things like that. So that's another area you can look at to just sort of assess. Obviously, it's not going to be tell you how well it's going to actually perform, but it's one way of assessing that.
Yeah, Inception score, Synchorn distance, all kind of distance metrics in the feature space. I agree. That's another way to mention.
Great. We have a great question from Pavan. On one side, we have generative models, GANs, VAEs, that can learn data generation from limited real-world data. On the other hand, we have simulators designed by handwritten rules, but takes lots of time. What do you think the future for data generation is going to be?
That's an excellent question. It's even with GAN generation techniques. I mean, I did mention some works like semantic GANs and dataset GANs and so on, but they're still very limited. So the main challenge is extracting. Like, you can generate very realistic images with something like style GAN and things like that, right? First problem is getting a label is going to be a problem, right? There's limited work out there, and they also work in limited capacity. So getting label is still going to be a problem with these approaches. And even if you get some of the labels, there's no way to ascertain the performance, right? Like when you actually have this synthetic data being generated, first of all, some of these images are very object centric, right? They don't really cover the entirety of the scenes. So most often is there is like one face or one car in the scene. So we want to generate like the full scenes. And when you generate full scenes, that's when you start getting into this semantic mass as a conditional generation or some kind of sketches. So even that is not that's not as cheap as people perceive it to be. So in terms of the future, I think the future is best of both the worlds. Like, I think the future is fusion between rendering engines approaches and again approaches, and figuring out where generative models are better and where engines are better, and then trying to combine best of both to create more hybrid models for generation.
Yeah, and one example I think that might work here is, you can imagine that the simulation engine can generate semantic masks, and then you can use GANs on top of that to generate
Yep.
realistic looking. And
Yep.
there's papers that have shown this to be an effective
Yep.
approach as well. So this sort of
That is
goes in line with yeah.
an excellent example of the fusion that we just.
Exactly. That's a great question. Okay, we have another question from Harsh, who asks, how can you give some pointers how to incorporate synthetic data sets into simulation overlays with real life images? Can they be made adaptable based on feedback loops? So I think maybe Harsh is going into more around sort of an RL framework. What do you think here in terms of that question?
I think this might be true. To answer the first part of his question, taking in real images and implanting synthetic images is not an easy problem either. I mean, either if you do it with no regard to context, by all means, what you're really doing is domain randomization at that point. So when you're doing domain randomization, it's going to perform like domain randomization. and not necessarily what you're not going to get anything win out of these real backgrounds. If you want to get a win out of these real backgrounds, you need to make careful placements or where you respect the context rules. And that's not an easy problem, right? And it's you can use some techniques to figure out uh, uh, where the roughly the objects are located and things like that. But that's when we start getting into some of the supervised domain, right? So that's my 2 cents. I mean, I don't know if it's any better than just doing the typical synthetic data it's done. In terms of feedback loop, I think you are alluding to something like reinforce, right? So when you have actually some kind of downstream task, or you have a validation test, validation or test set, you can use that signal to see how well we are performing on that, and use that signal to automatically create scenes. But that technique or that feedback loop it can be applied irrespective of whether we take in real images or not.
Great. All right, so let's go to the next question here. This is from Patrick, and he asked, what challenges do you see associated with scaling the distribution matching techniques or domain adaptation techniques from few parameters, rotation scaling to hundreds of diverse parameters that are needed to represent the complex scene?
Yeah, that's a great question. I think what Patrick, I believe, is alluding to more like metasim kind of approaches, where you're trying to learn the optimal distribution of parameters of the rendering scenes, such that the rendered scenes match the distribution of real data. And indeed, in the original work that I was part of, we did do it for just rotation and rotation and position. However, in order to really scale it, we have to identify the bottleneck in the system. So in that system, the bottleneck was lack of differentiable renderers. So including a better rendering engines which are differentiable, can actually truly scale that kind of methods, combined with the modern system design, right, where you can parallelize renderings across multiple machines. So with multiple machines parallelizing with some of the tech which we actually all already have or working on at AI.Reverie, to scale these rendering across multiple machines, and use of differentiable engines, can really truly scale this method to a point of full adoption. Because at that point it's just a bunch of multiplications, and that we are pretty good at this point.
Great. All right. So Christian asks, EO/IR is a popular sensor type in remote sensing, and it seems most of the work on synthetic data has been done in this area. Do you know of any research in other remote sensing technologies such as LiDAR, radar, terahertz, etc.? So anything that pops in your mind, Aayush, about work, especially with LiDAR, you have a ton of stuff in self-driving cars and stuff like that. So
Yeah.
anything you can share with the audience here?
Yeah, so that's a good question. I have some experience as well with point clouds and LiDAR. But one of the most compelling work I've seen recently in this domain is LiDAR sim. That the work that was published through Uber, and that's something I would point on to look into. It's called LiDAR sim, and they look into the domain gaps and how to properly simulate build LiDAR simulators that matches the distribution of the real data. And the work was pretty compelling. They have gotten some really good results. So that would be one. I'm seeing so much work happening in synthetic data. There's people are just going in every domain, and trying to see how can synthetic data help them.
Great. So we've got another question here that I think is a good one to just sort of address. Is there synthetic data methods used to generate audio, video data sets in addition to images? So it might be worth just talking about how synthetic data goes beyond computer vision as well.
Yeah. I don't personally have an experience with synthetic data beyond computer vision. Because or even we do object tracking and all kinds of gesture recognitions and things like that. But I think audio, right? So video is a great example. I mean, we have done a lot of videos, obviously, but that's still computer vision. But beyond all that, in terms of audio and NLP, I think, or text, for example, right? I think it's a very exciting area, especially when there's less. So we're talking about this domain gap, right? I perceive that there will be different kinds of domain gap. There will be some challenges there, but not as the same challenge that we say in vision. I cannot remember a work on top of my head, but I'm sure there, some of
Yeah.
the principles of synthetic data generation and some of the things that we have developed for vision can clearly be extended to audio and to text, for instance.
Yeah, and I just want to also highlight that there are some really cool things happening in the healthcare space, especially in terms of dealing with issues with privacy around electronic health records. So, synthetic data is just data that's just been generated either from algorithm or software, if you think about it. In the context of what we do, we obviously focus on computer vision, but you can imagine, when it comes to data sets that are very private, such as electronic health records, those things are super important to be able to generate synthetically if you want to help, bolster the distribution of your data. So I think and then there's in audio as well. There's some really good work in those areas as well that's worth looking into. Okay, great. So, and last question, I think the audience is really, would benefit from understanding is what kind of use cases do you find synthetic data to be super useful for? And what are the sort of things that you're seeing that really excite you as ways of solving problems with synthetic data?
So synthetic data can be useful for many kind of situations. Let's deal with the situations where it's pretty good, like it is on par or at the same level as real data. So that would be retail, or retail applications, or for example, security applications. I've seen, or even things like sign detection or road segmentation. I've seen synthetic data to be performing really well. So definitely that's exciting, and that can be used as we speak right now with all the state of the art that has been developed. To me, exciting things are around where it's most challenging, right? So to me, the most exciting application of synthetic data would be around these rare scenarios, really, right? Like these rare scenarios, these it really is the place where real data really fails. Where it's very hard to figure out the real scenarios, or even if you can't wait a long time to just for rare event to happen, right? You have to capture the data, and that's where synthetic data really shines. So to me, that's a very exciting avenue.
And I would almost say that, with enough effort, almost any problem can be tackled with synthetic
Yeah,
data. Also think
I
about
agree.
synthetic data technology that can scale much faster than the human
Yeah.
labeling process. In general, okay, so this is all we have in terms of time for questions. Thanks to the audience for asking so many great questions. Really excited to have been able to answer some of them. So I hope you enjoyed it, and I hope to see you all soon in another webinar. So thanks for coming by, and hope you enjoy the rest of your day. And thank you, Aayush, for joining us on this conversation.
Thanks for having me, Daeil.